Good afternoon or good morning, everyone. Welcome to the online logic seminar on foundations of mathematics. So this is a series of seminars organized by Wuhan University. Today, it's my pleasure to introduce Dr. Anton Freund. He graduated from Leeds in 2018 under the supervision of Michael Rathjen, and now he's working in Darmstadt as a postdoc. So without further ado, let's welcome Dr. Freund to give his lecture. Please.
Thank you very much. Thank you very much. Thank you very much for the kind introduction, and thank you for the invitation. It's a pleasure and an honor to be here. So I will speak today about well-ordering principles and the uniform Kruskal theorem. And the idea is that this connects several areas, and that I will also give an introduction to some of these. So well-ordering principles specifically connects ordinal analysis with reverse mathematics and computability theory, so different approaches within mathematical logic. And Kruskal's theorem is a theorem about finite trees, so that's from combinatorics. One of the basic ideas of ordinal analysis, sorry, I'm just trying to switch to the next slide. Okay. One of the basic ideas of ordinal analysis is to measure the strength of theories and of mathematical theorems using ordinals. So ordinals are special representatives for well-orderings. And maybe just to recall, a well-ordering is a linear order in which you have no infinitely descending sequences. And by the size of these well-orders, you can measure, as I said, the strength of certain theories and statements from mathematics. I don't want to go too much into the technical details, but in order to see something concrete, I still want to recall maybe the most famous ordinal that's being used in ordinal analysis, and that's this ordinal epsilon 0. And I want to present two perspectives on this. So one perspective is from set theory. In set theory, you have something called ordinal arithmetic. So you can take arithmetical operations such as exponentiation of ordinals, extending the usual operations that we know on natural numbers. And if you have these definitions from ordinal arithmetic, then you can characterize this ordinal epsilon 0 as the minimal fixed point of ordinal exponentiation, say to the base omega, where omega represents the ordered structure of natural numbers. However, you can also describe epsilon 0 in a more concrete way, and that's actually the description that will be more important for us today, namely the ordinals that make up epsilon 0, so the ordinals below epsilon 0, they can be represented by terms. And in order to make that precise, we have to simultaneously generate these terms recursively and inductively define an order relation between the terms. So the recursive clause that generates the terms is we start with a constant symbol for 0, so that will be the smallest term in this ordering. And then whenever we have terms alpha 0 to alpha n in weakly decreasing order, then we can form this expression here, this sort of exponential normal form here, and that will also be a term that represents one of our ordinals. And then simultaneously here we define this order relation, namely the order relation is simply the lexicographic order on the exponents. And since the exponents are also terms and we need to compare the exponents in order to determine the lexicographic order, this means that we have recursive calls. So this order relation here is defined by induction over the complexity of terms. Once again, if you do come from set theory and if you are comfortable with these operations from ordinal arithmetic, then it makes sense to think of this expression here as something like a Cantor normal form from set theory. But this connection is not actually strictly required for this talk. Maybe it's good to look at an example. So as I said, we have this term 0 here. And then whenever we have a sequence of terms, so in particular a single term, we can form this exponential expression here, omega to the 0. And then we can also form sums of these. So we already have a term omega to the 0 now, so we can take this to the omega again and add some other terms to it. And then, of course, you can introduce abbreviations that correspond to, in a sense, to the usual laws of arithmetic with exponentiation. So, for example, something to the 0, you would write this as 1. And since you have 2 summons 1 here, you can write simply a 2 here. And then if omega to the 0 is 1, then this expression here will be omega to the 1, which is simply omega itself. So here on the left side, you could more briefly write omega plus 2. And on the right side here, you would write omega square. And then this expression on the left is smaller than the expression on the right. In order to determine this, you have to compare lexicographically. So you have to compare the first exponent on the left, first of all, with the first exponent on the right. And then you see that this here corresponds to 1, while this here corresponds to 2. So the left side is actually smaller than the right side. Okay, now that looks a bit complicated, maybe syntactically, but actually in order to follow the talk, we don't need to know much about this. All we really need to know is that we have a very concrete ordering. It's built out of terms, and we can primitive recursively decide whether a term belongs to our linear order, and we can also primitive recursively decide the order between 2 terms. So now that we have this complicated ordering epsilon 0, we can formulate one of the founding results of ordinal analysis, which is due to Gerhard Gentzen from the 1930s. And this result is concerned with the piano arithmetic, or PA. So that's probably the central system of first order number theory. So the paradigmatic system that allows us to reason about natural numbers, about finite objects. And the claim in this theorem of Gentzen is that this theory, piano arithmetic, it cannot prove that this order epsilon 0 is well-founded. And to be a bit more precise, so usually if you say that something is well-founded, then, as I said, you mean that there are no infinitely descending sequences. In order to express that, you would have to quantify over infinite sequences, so you have to quantify over infinite objects. That's something that piano arithmetic cannot do because it only speaks about finite objects, about natural numbers. So you have to give some alternative sense to this claim that epsilon 0 is well-founded. And the way to make this precise is to say that there are no primitive recursive sequences of ordinal terms that descend forever. So whenever you have a primitive recursive sequence of terms, then some term in the sequence will be smaller than the following term, smaller or equal. Good. So Gentzen gave at least 2 different proofs of this result, and I want to present one briefly because we will see different variants of this proof later, and it might be interesting to see how these different variants relate and what changes between them. So we want to prove that something is not provable in piano arithmetic. And the idea is to reduce to a statement which we already know to be unprovable. And that comes from Gödel's theorem. So Gödel's incompleteness theorem tells us that the consistency of piano arithmetic is unprovable in piano arithmetic. So if working in PA, we can now show that the well-foundedness of our ordinal epsilon 0 implies the consistency of PA. Then since PA cannot prove the consistency, it follows that PA cannot prove the well-foundedness of this complicated ordering epsilon 0. Good, so how do we do this reduction? Well, very roughly, the idea is that we label proofs by ordinals below epsilon 0. So to each proof, we would assign an ordinal below epsilon 0, such that the following holds. Whenever we have a proof of contradiction, then this proof will have a certain label. And the claim is that we can transform this proof of contradiction into another proof of contradiction that will have a smaller ordinal label. I wrote purported here because, of course, we don't have proofs of contradiction at all. So it's kind of a hypothetical argument. You imagine that you have a proof of contradiction, and then you argue that whenever something like that would be given, then you could transform it into something that has a smaller label. And now we can conclude the consistency of piano arithmetic as follows. So assume towards a contradiction that there is a proof of contradiction in piano arithmetic. And then by repeating this procedure here, we could generate a proof with a smaller label, and then yet another proof with a smaller label, and yet another one with a smaller label. So in this way, we could generate an infinite sequence of proofs of contradiction, which have smaller and smaller labels. So we would get an infinitely descending sequence of ordinal labels below epsilon 0. And that cannot be, since we have assumed that epsilon 0 is well-founded. And by the way, if you have any questions in between, then please do interrupt. That seems to be fine now. Okay. Yeah, so why is this result of Gensen interesting? Well, Gödel's theorem tells us that there must be certain statements which are unprovable in systems for the foundations of mathematics, such as piano arithmetic, or also Zermelo-Fraenkel set theory. And one question that has been and still is very influential and fruitful in mathematical logic is whether there are any natural statements with this property. So by natural, I mean statements that actually occur in mathematics that are not constructed by logicians, such as the consistency statement from Gödel's theorem. And I would say that Gensen's theorem brings us quite a bit closer to such a mathematical independent statement, because this ordinal epsilon 0, it's quite natural. It's related to exponential notation as we have it under natural numbers, and well-foundedness is also a property that we encounter frequently in mathematics. So the claim that epsilon 0 is well-founded, I would say it's certainly closer to a natural mathematical statement than the consistency statement itself. However, it would of course be nice if we could make this still more natural, and if we could somehow connect it to a theorem that really appears and is prominent within core mathematics. And it turns out that we can. Namely, piano arithmetic cannot prove the binary Kruskal theorem. So what do I mean by this? Well, Kruskal's theorem is a theorem from combinatorics, and it says that whenever you have an infinite sequence of finite trees, T0 with T0, T1, and so on, so these are trees, then you can find a smaller index I such that the tree Ti in this sequence embeds into the tree Tj that comes later in the sequence because it has a larger index j. So in any infinite sequence of trees, one tree can be embedded into a later one. And here I'm considering Kruskal's theorem for binary trees only, so this becomes an even simpler, even weaker statement. And even this weaker version of Kruskal's theorem for binary trees, I claim, is unprovable in piano arithmetic. So I should say two more things to make this precise. First of all, if we want to work in piano arithmetic, then as before, we cannot consider arbitrary sequences. So let's restrict to primitive recursive sequences. It just makes the theorem weaker and hence the independence result more impressive. And secondly, I would like to say that I'm considering trees that have a root and that are ordered in the sense that you can distinguish left and right subtree. So the theorem, or this corollary here, actually does also hold if you consider unordered trees, so trees where you cannot distinguish left and right subtree. But this is quite a bit more difficult, and there is some work by Andreas Weiermann and his co-authors on this unordered version of the independence result. But for ordered trees, it's not that hard to get this corollary. Namely, we can deduce it from Gensen's result from ordinal arithmetic as follows. So the idea is that we define a primitive recursive function that goes from ordinals below epsilon 0 to these finite binary trees. So yeah, let's maybe first see what this function does. Well, these ordinals below epsilon 0, except for the 0 ordinal itself, and they were exponential sums, so they can be split into a sum where this here is the first part of the exponential expression, omega to the alpha, and then beta is just the remainder of the sum. And recursively, you can already assume that that you know what this function that you want to define does on alpha. So it assigns some tree f of alpha to alpha, and you can also assume that you know what it does on beta. So it will assign some tree f of beta to beta, and then to define the value of f on this sum here. So on, let's say, an arbitrary element of f epsilon 0, you simply take these two trees that were previously constructed, you add a new root node, you connect a new root to these two trees, and then this bigger tree here will be the value of f on this new exponential expression, omega to the alpha plus beta. And what you can check quite easily is that this map is order reflecting, in the sense that if the tree f of alpha embeds into the tree f of beta, whatever that means, I didn't give the precise definition. If this tree f of alpha embeds into f of beta, then the ordinal alpha will be bounded by the ordinal beta. And now we already know from Gensen's result that piano arithmetic cannot prove the well-foundedness of epsilon 0. So in order to show this new unprovability result here, it suffices to reduce the well-foundedness of epsilon 0 to this version of Kruskal's tree theorem. And that's done as follows. So consider an infinite sequence of ordinals below epsilon 0, then use this function f here to transform it into an infinite sequence of binary trees. Then by Kruskal's theorem, you will know that some earlier tree embeds into a later tree. But then, since we have just discussed that this map is order reflecting, we will know that the ordinal from which this earlier tree comes is bounded by this later ordinal that corresponds to the later tree. So in our sequence of ordinals, we will have an inequality of this form, and that means precisely that epsilon 0 is well-founded. So maybe to give a bit less technical explanation, the idea is simply that we can look at, so ordinals are represented by terms, and we can look at terms as trees, so in a sense as the construction trees of these terms. And the idea is that the order relation between the ordinals can be related to the embeddability relation between these terms considered as trees. Okay, and so now we have a genuinely mathematical independence result from piano arithmetic. Good. So so far we have been very much in the traditional realm of ordinal analysis, namely in the realm of finite objects, of natural numbers, of first order arithmetic. And I think that this realm is very, very interesting. First of all, for philosophical reasons. So for example, in the context of Hilbert's program, this realm of finite objects of first order arithmetic plays a particularly important role, but also for technical reasons. So here the point is that if you have infinite objects involved, then you have more objects, and so you also have more invariants. So for example, to make meaningful distinctions between different infinite objects, you could use the notion of relative computability. So if some infinite object is computable relative to another one as oracle, then one of them would be simpler than the other. And in the context of finite objects in the, say, traditional domain of ordinal analysis, many of these invariants are not available. And I think that's an interesting technical challenge to see whether you can still prove independence results without some of the invariants that you would use in other domains. Nevertheless, of course, the infinite is an extremely interesting topic in mathematics, and I'm particularly interested in connections between the finite and the infinite. So I want to bring the infinite now into the picture, and for that purpose, I want to change setting a bit. Namely, I want to switch to second order arithmetic and reverse mathematics. I think you have already had quite a few talks that go in that direction in the seminar. So I will keep this brief, but I still want to provide a minimal introduction for the purpose of this talk here. So as I said, we are in second order arithmetic now. And the point is that in this setting, we can quantify, we can talk about natural numbers that represent finite objects as before, but now we can also quantify over subsets of the natural numbers that represent countable collections of such finite objects. Let me present two of the principles that will be important in the following. So the first one is arithmetical comprehension. And this principle says that whenever you have a formula phi without set quantifiers, so by that I mean it does not quantify over these subsets of n, it can only quantify over finite objects. Such a formula is called arithmetical, and arithmetical comprehension says that for any of these formulas, there is an x such that the set x consists precisely of those n that satisfy phi. So maybe we could add that what this means is that x is the set of n such that phi of n, and arithmetical comprehension says precisely that this set here exists. And then I also want to look at arithmetical recursion, and that's simply the principle that you can iterate this arithmetical comprehension principle along the natural numbers. Namely, it says that you can form sequences of sets indexed by the natural numbers such that the n plus first set in the sequence is defined by some given formula phi relative to the previous set in the sequence. And then if you want to be precise, you can code these infinitely many sets xk into a single one, but that's not really necessary for the present talk. Okay, so arithmetical comprehension, you can form sets of this form for phi that is not too complicated, and arithmetical recursion along n, you can iterate this process along the natural numbers. And I think one particularly intuitive approach to second order arithmetic that will also be important in the following is omega models. So the idea is that in second order arithmetic, you have on the one hand the natural numbers, and on the other hand subsets of the natural numbers. So in a model, you have to decide how to interpret each of these two. And in an omega model, the idea is that you interpret the natural numbers simply as the standard model m. So you don't admit any non-standard numbers. So on the level of finite objects, everything is standard and relatively straightforward. But on the level of the infinite objects, you don't necessarily take the full power set, you don't take all subsets of the natural numbers, but you take some subset of the power set. And this subset of the power set is then what gives your omega model. And intuitively speaking, the idea is that this collection M, the subset of the power set, it tells us which infinite sets we need to make a statement true. So you can, if you have a statement of second order arithmetic, then you can evaluate whether it holds in an omega model. And if it holds, then this omega model M would have all the infinite sets that are necessary to make this statement true. And maybe it's even better to say that it doesn't tell you which infinite sets we need, but it tells us which closure properties of infinite sets we need. And now I want to make an observation that sort of shows a crucial difference between ordinal analysis and reverse mathematics. And this is that the statement that epsilon 0 is well-founded, it holds in all omega models. And that's because it does not assert the existence of any infinite sets. So it says that there is no infinitely descending sequence in epsilon 0. So that's negation and then an existential quantifier, or in other words, it's a universal quantifier. So if there are fewer infinite sets, then this statement becomes easier. It does not assert that there are any infinite sets. And so this well-foundedness statement holds in all omega models. On the other hand, the principle that we saw on the last slide, arithmetical comprehension, it does not hold in all omega models, because you can show that it asserts, for example, that Turing's halting set exists. And so if you build an omega model that consists purely of computable sets, then the halting set will not be present, and then arithmetical comprehension will not hold in that omega model. Okay, and now we can see whether we can somehow bridge this gap. So the gap between ordinal analysis, things that hold in all omega models, and statements from reverse mathematics and computability theory that don't. And the idea is that in order to bridge this gap, we now need to consider transformations of orders. So previously we considered single orders, and now we want to consider transformations of orders. So we call that epsilon 0 was the minimal element of this set here, the minimal fixed point of ordinal exponentiation. And now it turns out that this set of fixed point is actually unbounded. So there are arbitrarily large fixed points. In fact, there are closed. It's a closed and unbounded, so a club class of ordinals. And since it's unbounded, there's a strictly enumerating, a strictly increasing enumeration of that set. And this enumeration I want to denote by gamma goes to epsilon gamma. And epsilon 0, the ordinal that we saw before, would be the first element in this enumeration. And now, not unlike what we saw before for epsilon 0, ordinals below an arbitrary fixed point epsilon gamma can be represented by terms as well. And the only change is that we throw in these new terms epsilon beta for beta below gamma. So in order to represent the gamma fixed point epsilon gamma, we throw in all the previous fixed points. And one important thing to note is that, well, as before, these exponents here, they are terms. So there's some recursive construction going on here. But this beta here is not a term. It's an external ordinal below this ordinal gamma that is given. And since these epsilon beta are indexed by external objects, you should view them as constant symbols. So you could also say that this is simply a relativization of the representation system for epsilon naught that we saw before. And now the crucial observation is that now that we consider transformations rather than single orders, we actually do get statements about the existence of infinite sets. Namely, if we look at a statement that this map, gamma goes to epsilon gamma, preserves well-foundedness, in the sense that if gamma is well-founded, then epsilon gamma is also well-founded. And then this does imply the existence of infinite sets. And to see that, we should look at the contrapositive of the statement. Namely, the contrapositive says whenever we have an infinitely descending sequence in epsilon gamma, then there is also an infinitely descending sequence in gamma. So if epsilon gamma is not well-founded, then gamma is not well-founded. And this there is here is this existential claim about infinite sets that's contained in these statements about order transformations. Good, so what does that mean for the previous results from ordinal arithmetic? What becomes of them? Well, there's this theorem here, which was proved by Alberto Marcone and Antonio Montalban, and then by different methods by Bahari Afshari and Michael Rathjen. And this is now a typical result of reverse mathematics. Namely, we work over a weak base theory, and we prove an equivalence between certain statements. And the equivalence now is between this well-ordering principle, so this statement that if gamma is well-founded, then psilon gamma is also well-founded, then this here is what we had before, this principle of arithmetical recursion along the natural numbers. So we can define sequences of sets in a certain way by recursion along the natural numbers. And then these two are also equivalent to a third statement, namely the statement that every subset of the natural numbers is contained in some omega model of recursive comprehension, so of the other principle that we saw before. And maybe about 3, I should make 2 things precise. First of all, we now work in a specific meta theory, so 3 should be formalized in that meta theory, and that means that we should consider countable coded omega models. But I don't want to go into these technical details more. And secondly, as part of 3, I also want to assume that arithmetical comprehension holds. So not only does it hold in omega models, but it also holds sort of in the real world. And yeah, I think that's quite interesting, because now we have a statement that's simply the relativization of this statement from Gensen's result from ordinal analysis. But we also have this statement here, which is very typical of reverse mathematics. And what's also telling is that there are actually 2 very different proofs of this theorem, of this equivalence here, namely the one by Marcone and Montalban uses a computability theory, and the other one by Afshari and Rathjen uses proof theory. So yes, I think it's nice to see that these 2 approaches come together in that result. Okay, now previously, okay, I want to briefly show how this is proved. So it's not hard to see that 2 and 3 are equivalent. So I don't want to say anything about that. And it's also not too hard to show that from 2 or 3 you can derive 1. The crucial direction is to go from 1 to 3. So given this statement about the preservation of well-foundedness, how do you pull a set existence statement out of that? And for that, the idea is to use the notion of omega proof. So an omega proof is a tree. You can also write normal proofs as trees, where you go from axioms to the conclusion that's written at the root of the tree. But in an omega proof, what's special is that if you want to derive a statement of this form here, for all n, for all natural numbers n, phi of n wholes, then you can derive this from infinitely many premises. So if you have derived phi of 0, and you have derived phi of 1, and you have derived phi of n for each n, then you can conclude that this universal statement holds here. So yeah, this is an infinite proof rule now. And of course, you cannot use these infinite proofs in practice because you couldn't write them down, but they're an interesting theoretical tool. Also, don't worry about this gamma. This comes from, so the setting for this whole approach is sequent calculus, and in sequent calculus, you always have these big disjunctions. But the main point is really that from phi of 0 and phi of 1 and so on, we go to this universal statement for all n, phi of n. And now, just as there is a completeness theorem for usual proofs in predicate logic, there's also a completeness theorem for these omega proofs, and that's the Schoenfield completeness theorem. Now, completeness as a special case, and actually the central special case of completeness, you get the statement that if a theory is consistent, then you get a model for this theory. And the Schoenfield completeness theorem allows you to do exactly the same, but for these infinite omega proofs and omega models. Namely, it tells you that if there is no omega proof of a contradiction from, this is arithmetical comprehension, then you get an omega model of arithmetical comprehension. And an omega model of arithmetical comprehension is precisely what we wanted for the theorem on the previous slide. So the only thing that remains to be done now is to exclude that there is an omega proof of contradiction from arithmetical comprehension. And showing that there are no proofs of contradiction, so that certain systems are consistent, that's precisely what ordinal analysis does. So namely, as I said, we want to show that there's no omega proof of contradiction. And what we can do is we can simply relativize Genson's ordinal analysis to a given omega proof. So previously, Genson was concerned with finite proofs in piano arithmetic, but if we relativize his arguments, then we can make them to work with an arbitrary infinite omega proof as input. And where Genson previously used his ordinal epsilon 0, we must now, after this relativization, use this transformation gamma goes to epsilon gamma. So yeah, maybe I should say again that it's really not the technical details that I want to explain here. It's simply the general idea that you can take traditional proofs from ordinal analysis and you can relativize them in a certain way, and then from this relativization you get a statement in the context of reverse mathematics. Good. So now, previously, from this result of Genson, we derived a mathematical independence result related to Kruskal's theorem. So now the question is, from this new relativized reverse mathematics result, can we maybe also get a more mathematical version of that is related to Kruskal's theorem? And it turns out that we can. So for this purpose, I want to introduce a new notion, namely the notion of well partial order, abbreviated WPO. So a partial order X is called a well partial order if the following holds. Whenever you have an infinite sequence of elements in your order, then there are indices I smaller than j, such that the earlier element xj of your order is bounded by the larger element, by the later element xj in your sequence. And so Kruskal's theorem, as we saw it before, just says that trees together with the relation of embeddability form a well partial order. And now here the idea is to consider trees with labels. So more specifically, I want to write B of x for the set of binary trees as before. But now at the leaves only, you can have elements of x as labels. And then by this previous theorem, by the relativized ordinal analysis, together with the result of Diana-Schmidt, you get the following corollary. So again, over this weak-based theory of reverse mathematics, the following are equivalent. The first statement is that if x is a well partial order, then the binary trees with leaf labels from x do also form a well partial order. So that sounds a bit complicated. The shorter way to state it is simply to say that Kruskal's theorem holds for binary trees with leaf labels. And this version of Kruskal's theorem with leaf labels is now equivalent to arithmetical recursion along the natural numbers. Yeah, we have a result from reverse mathematics now that proves an equivalence between one version of Kruskal's theorem and a typical set existence axiom. Okay, so now after these kind of specific results, I want to say a bit about the state of the literature and the broader picture. So a statement of this form here, some transformation of an order gamma into another order d of gamma preserves well-foundedness, where typically the transformation d is computable. Such a statement is called a well-ordering principle. And to be precise, you should maybe call it a well-ordering principle of type 1. And the example that we saw before took gamma into epsilon gamma, so into this relativization of Genson's ordinal. But now, in addition to this specific transformation gamma to epsilon gamma, you can well consider many other such transformations, many other well-ordering principles. And there have been equivalences between this type of well-ordering principles for very natural transformations D, and important set existence axioms from reverse mathematics. So I just want to name them. The first of these is arithmetical comprehension is equivalent to a well-ordered principle. That's the first result in that direction. It's due to Girard and Hurst. And then arithmetical transfinite recursion, so ATR0, is also equivalent to a well-ordered principle. And then the existence of omega models of certain set existence principles, such as, for example, bar induction. These statements about the existence of omega models are also equivalent to well-ordered principles. And then you can also find versions of Kruskal's theorem or similar combinatorial statements that are also equivalent to these well-ordered principles. So there are a lot of interesting results here, but there's also a principle limitation. And to discuss this limitation, I want to look at another very important principle from reverse mathematics, namely the principle of pi-1-1 comprehension. So we already saw arithmetical comprehension, and the only difference in pi-1-1 comprehension is that now in the comprehension formula, we can have one quantifier over infinite sets. So one quantifier over subsets of the natural numbers. And then in the rest of this comprehension formula, there should be no further set quantifiers. So let me maybe write this as well as I wrote it before. So what pi-1-1 comprehension says in a bit more intuitive terms is that these sets X, which consist of all n, such that such a universal statement, such a universal statement holds, these exist. So sets with a very complicated definition exist. And now the point that I want to make here is that these well-ordering principles here, so some transformation gamma goes to T of gamma preserves well-foundedness, they are always what one calls a pi-1-2. So this means they are a statement of the following form, and they say for any subset X of the natural numbers, there is a subset Y of the natural numbers such that some property without further set quantifiers holds. And it is known that pi-1-1 comprehension, so the principle which asserts the existence of these complicated sets, cannot be equivalent of any statement of this form here. So once again, pi-1-1 comprehension, which is a very important axiom in reverse mathematics, cannot be equivalent to one of these type 1 well-ordering principles that we have been looking at so far. And since I have already mentioned or stressed the words type 1 a few times now, the way out of this limitation is also visible on the horizon, I guess. Namely, in order to overcome this limitation, we will want to look at well-ordering principles at higher type. So previously, the input of our well-ordering principles was a single order, and the output was also a single order. And now in these higher type principles, we want to take as input a transformation D, no longer a single order, but a transformation of orders. And then from that transformation, we will want to compute an output f of D. And this output f of D can actually be a single order again. So for the type of functionals, the type of the argument is more important than the type of the value. But the crucial point is that we now want to look at transformations that will themselves take transformations as input. Now, the first thing to consider is maybe which transformations we want to allow as input. Of course, we could simply allow all transformations of linear orders D as input here. But this is not actually the way that we will go. And this has the following reasons. So we want to compute the output of these higher well-ordering principles in a very concrete sense. And of course, there are models of computation that take arbitrary, infinite, higher type, uncountable objects as input. But I want to look at very concrete computations here. And for these concrete computations, it's usually required that the input can be has finite approximations. And so this this input D here should be determined by certain finite approximations, or in other words, it should be continuous in a suitable sense. And what exactly this means, you can see on this slide here. But that's quite technical, so I don't want to go through all the details. I just want to mention some main points. So one point is that one will now work with certain notions from category theory. So in particular, we will want to consider the ordinals as a category, where we consider ordinals as objects, but then also morphisms between these objects, and these morphisms are the strictly increasing functions between ordinals. And now a notion which is due to Girard. I wrote essentially Girard because I formulated the definition in a rather different way. But a concept that's due to Girard is the concept of dilator. And such a dilator consists of a functor from ordinals to ordinals and a natural family of functions that compute certain supports. So yeah, as I said, let me just summarize what the main points are. The main points are that this D here is a transformation of ordinals into ordinals as before. So it's one of these well-ordering principles of type 1. And then what do these support functions do? Well, D of beta is one of the values of this transformation here. And to each element of this value D of beta, the support function sub beta should assign a finite support, so it should assign a finite set of ordinals below beta to this element here. I think the best way to think about this is probably that the elements of D of beta are terms, and this support picks out the constant functions that occur in different terms. Okay, but really all we need for the following is that a dilator is a special, say particularly uniform transformation of well orders, and each element of a value has something that's called its finite support. And one thing that I just want to mention is that since these dilators are continuous in a certain sense, so the continuity property is here, but I don't want to spell it out now. Since these are continuous in a certain sense, they are determined by their restrictions to finite objects, and that makes it possible to represent them in second-order arithmetic. So there's no need at this point to go to higher order arithmetic or set theory. But again, I don't want to spell out the technical details here. Let's maybe look at an example of such a transformation. So here I have a transformation D, which transforms a given order gamma into another order, and namely this output on input gamma is the order 1 plus gamma square, and you can represent that in a rather straightforward way in set theoretic terms. Namely, 1 is the singleton order that contains a single element 0, and then gamma square consists of all pairs of ordinals below gamma. Then, yeah, let's maybe forget about this now. This is because D is supposed to be a functor, so it acts not only on objects, but also on morphisms, and here you have the two clauses for this. But what I do want to point out is these support functions here. So the support of gamma, once again, it should take elements of D gamma as input, and it should give finite subsets of gamma as output. So what does it do? Well, in D gamma, we have two types of element. We have this element 0, and this element 0, it doesn't really depend on anything, so we just say that it has empty support. And then we have pairs of elements, pairs of ordinals below gamma, and the support should say on which ordinals these pairs depend, and well, they simply depend on their components. So the general definition is somewhat lengthy, but in concrete cases, it actually looks quite natural, I think. Okay, and now let's come to one of the main notions of this talk. This is the notion of Bachmann Howard fixed point. So yeah, the idea is that we want to take an arbitrary order transformation as input, and then out of this order transformation, we want to generate another order as output. And this output is precisely what I call here a Bachmann Howard fixed point. So what is it? Well, it consists of an ordinal gamma, which is a fixed point of this transformation D, in the sense that there is what I call a collapsing function theta of this value D of gamma back into the input gamma. And the idea is that this collapsing function, it should preserve the order as much as possible. But as it turns out, it cannot always preserve the order. So what can we get? What does it mean that this collapsing function theta preserves the order as much as possible? Well, it means two things. So first of all, if sigma is smaller than gamma in the domain of theta, then the value theta of sigma will be smaller than the value theta of gamma. So that precisely means that theta is order preserving. But the point is that it turns out we cannot demand this all the time. So we demand it under a side condition. And the side condition is that we consider the support of the smaller element. And once again, the support is a subset of gamma. And then we ask whether for any element alpha in the support, this element is bounded by the collapse of the larger element tau. And if this is always the case, if all elements in the support are bounded by the larger value, then we say that the side condition is satisfied, and then we demand that our collapse theta is order preserving at that point. And then the second condition is maybe a bit less interesting. It simply says that whenever we have an alpha in the support of sigma, then this alpha should be bounded by the collapse of sigma. So that simply rules out some trivial examples. Yeah, but once again, what does this mean intuitively? It means that gamma is a fixed point of a given transformation D, in the sense that we have a collapse of D of gamma back into gamma that is almost order preserving in a suitable sense. Two things that I would like to point out is, first of all, this notion of Bachmann Howard fixed point is very much inspired by the so-called Bachmann Howard ordinal that appears in ordinal analysis, and more precisely by a particular notation system for this ordinal that was given by Rathjen. And secondly, as I said before, the side condition in one cannot be avoided. So we cannot assume that theta is order preserving all the time. And that's simply because it could happen that D of gamma is always strictly bigger than gamma, and then we cannot have a order preserving map from D of gamma into gamma. Okay, now I will get back to, I hope, slightly less technical things. Okay, first, maybe this is still a bit technical, but I want to show you what comes out of the example that we have seen earlier. So before, we have seen this transformation of gamma into an order D of gamma that was defined as 1 plus gamma square with certain support functions. And now I claim that this ordinal epsilon 0 that we already saw in Gensen's result, that this ordinal here is a Bachmann Howard fixed point of this particular D given here. So in order to show this, we must define a function theta from D of epsilon 0 to epsilon 0. And the idea is simply that we map this element 0 here to the ordinal 0. And then if we have one of these pairs here as the argument of our collapsing function theta, then we map it to this exponential expression here below epsilon 0. So epsilon 0 is a fixed point of this d here. And in fact, it's the minimal Bachmann Howard fixed point, because if you have any Bachmann Howard fixed point of d from above, then you can construct an embedding of epsilon 0 into this Bachmann Howard fixed point recursively by, I know there's no recursive call, but you can simply define it explicitly by these two clauses. So we don't have to look at the details, but what I think is very, very nice about this is that the ordinal epsilon 0 that we already know from Gansen's classical result turns up here again. And that actually, once one has mastered this somewhat abstract setting of delators, things become very simple, because well, epsilon 0 is quite a complicated object. We saw this simultaneous inductive definition of terms and then order on terms and so on. And I think that's quite a bit more complicated than this simple sum here. So 1 plus gamma squared, just a single point, and then pairs below a given object. That's a relatively simple object. And that out of this relatively simple transformation d here, we can sort of pull out this complicated ordinal epsilon 0 as fixed point. I think that's quite nice. Okay, so now I hope that it will get a bit less technical. Namely, I want to state the result that comes out from all this. So as I said before, Pi-1 comprehension is a very important principle from reverse mathematics. And it was sort of beyond the reach of this type of well-ordering principle that we saw before. But now that we have made this switch from simply transformations of ordinals into transformations of higher type that can take other transformations as input, we can actually characterize this principle of Pi-1 comprehension. And that goes as follows. So it turns out that whenever you have a delator d, so a suitably uniform transformation of ordinals, then any such delator d will have an initial Bachmann Howard fixed point. So in other words, a smallest Bachmann Howard fixed point, which I want to denote by theta of d. And it also turns out that the transformation of a given d into its Bachmann Howard fixed point theta of d is computable. And now we can formulate the equivalence. So once again, this is an equivalence that's typical of reverse mathematics, and so far that it's formulated over the usual weak-based theory RCA0. And it says that the following two things are equivalent. First, if d is a delator, then this fixed point theta of d is well-founded. And secondly, this principle of Pi-1 comprehension that we saw before. And once again about 1, so the transformation of d into theta d is computable. So just to have this transformation, we don't need any strong principles such as Pi-1 comprehension at all. The entire strength in 1 really lies in the claim that this computable order here is well-founded. Okay, now I want to give you a glimpse of the proof. And the proof relies on a previous result by Gerhard Jäger, which shows that this principle 2 here, Pi-1 comprehension, is equivalent to a certain statement from set theory. And this statement says every set lies in a transitive model of Kripke-Platek set theory. Now, I believe that there has been an introduction to Kripke-Platek set theory in the talk by Fedor Pakhomov sometime in autumn in this seminar. But anyway, it's not important what precisely this theory is. The thing that I want to point out is that, well, originally in Gansen's result, we were talking about consistency, and consistency is, because of the completeness theorem, equivalent to the existence of some arbitrary models. Then a bit later, we have been talking about the existence of omega models. So a somewhat stronger notion in arbitrary models. And here we talk about transitive models of set theory which are still, so transitive models here, still a stronger notion than omega models. So yeah, in order to show that 1 implies 2, it's now enough to show that 1 implies 3. So somehow out of this statement about the preservation of well-foundedness, we now have to pull out these transitive models of a certain set theory. And I want to briefly explain how this works. Namely, the idea is to look at something that's yet more general, let's say, than omega proof. And for this generalization, I want to look at Gödel's constructible hierarchy of definable sets L. And based on this constructible hierarchy of sets due to Gödel, you can introduce the notion of L alpha proof for an ordinal alpha. So L alpha is now a stage in this constructible hierarchy of Gödel, and an L alpha proof is something very similar to an omega proof, namely, in order to derive a universal statement, you can use a rule that has infinitely many premises, and specifically it has one premise phi of c for each element c of the alpha stage of Gödel's constructible hierarchy. So the only thing that we have done in comparison to the omega rule is we have replaced a set of natural numbers by these stages of Gödel's constructible hierarchy. And now in the case of omega proofs, we had a completeness result that was proved by Schoenfield. And here we also have a completeness result that goes back to work of Girard, but I think that in this specific form for the constructible hierarchy, it hasn't been formulated before the paper that I wrote. And what the completeness result tells you now is that if there is no L alpha proof of contradiction in Kripke-Platek set theory, then if there's no proof of contradiction, you get a model. And in this particular case, this is a model of Kripke-Platek set theory, and it has the form L beta for some beta below alpha. So it's also a stage in Gödel's constructible hierarchy. And now for the proof that, for the theorem that we want to prove on the previous slide, we want to get transitive models of Kripke-Platek set theory. And we can get this by our completeness result if we can show that indeed there are no such proofs of contradiction. More specifically, what we need to show is that there cannot be proofs of contradiction for all ordinals alpha. So let's do that now, and let's see how the ordinal analysis and our notion of Bachmann Howard fixed point comes in. So aiming at a contradiction, assume that we have an alpha proof of contradiction for every ordinal alpha, and I want to call these proofs of contradiction P alpha. And now, since we work with relators, and these are objects come somehow from category theory, we have to make our constructions functorial, but that can be done. So the construction of Gödel's constructible hierarchy can in a certain sense be turned into a functor, and then our family of proofs P alpha can also be turned into a functor. And once we have done that, we see that the ranks of these proofs here will be bounded by the values of a delator D. And now, by the direction of the theorem that we want to prove, we know that this delator D here will have a Bachmann Howard fixed point theta of B that is well-founded, or in other words, an ordinal number. And the idea is now simply that we can use this ordinal number and known techniques from ordinal analysis in order to produce a contradiction and conclude the proof. A bit more specifically, we know that this ordinal number, this Bachmann Howard fixed point, comes with such a collapsing function here. And this type of collapsing functions is precisely what you need in the ordinal analysis of Kripke-Platek set theory, which is due to Gerhard Jäger. So using this collapse here, you can emulate this traditional ordinal analysis in our somewhat more abstract setting. And the conclusion of the ordinal analysis is that there's no proof of contradiction. In our specific case, that P, so the proof from our family of L alpha proofs at this Bachmann Howard fixed point cannot be a proof of contradiction after all. And then that's a contradiction to the assumption that all these proofs are proofs of contradiction. And so it concludes our proof. So yeah, let me give another summary. It does not involve these technical details. So yeah, once again, the idea is to relativize traditional techniques from ordinal analysis. Traditionally, they were used for single finite proofs, for single ordinal numbers represented by term systems. And now we relativize them to transformations of higher type, to transformations of other transformations. And we look at these functorial families of proofs somewhere in a set theoretic hierarchy. And by relativizing the traditional methods of ordinal analysis to these, we can ensure the existence of transitive models of set theory and hence of very complicated infinite sets. Now, in the final part of my talk, I want to give an application of this. And this is once again parallel to the applications that we had before. So from ordinal analysis, you get independence results or equivalences that involve well orders, ordinal numbers, transformations of these. But then it's nice to see whether you can turn these into more combinatorial, more mathematical independence results and equivalences. And in particular, one very promising route in that direction is always provided by this Kruskal theorem about finite trees. And it turns out that also for this extended abstract equivalence with power 1 comprehension, you can also find a very nice formulation of Kruskal's tree theorem that is equivalent to that. And this last part of the talk, I also want to point out, is based on a joint paper with Michael Rathjen and Andreas Weiermann. Okay, so let's look at finite trees once again, and now it's finally getting a bit more concrete again. And here the observation that I want to start with is that the finite trees arise as a minimal fixed point, namely as a fixed point of the transformation that takes a set or order X as input and gives the collection of finite sequences with entries in that set as output. And to see that the finite trees are a fixed point of that operation, it's basically enough to look at this picture here, because what you can see here is that in the upper half, you have a finite sequence of trees, T1, T2, and so on to Tn. So you have, in a sense, an element of the right side here, a finite sequence of objects. And to get an element of the left side, so to show that we have a fixed point, it suffices to combine this finite list of trees into a new tree. And you can do that simply by adding a new root node and connecting this root to the finite list of given trees. And similarly, you can construct other objects. So for example, if you want to look at the collection of finite sequences with entries in Y, then you can also construct them as the minimal fixed point of a certain transformation. So here, this is the transformation of X into one union Cartesian product of X and Y. And the finite sequences are the fixed point of this operation here because where these two expressions here correspond to the generators of finite sequences. So one is, once again, the singleton order, and this corresponds to the generator take the empty sequence. And then well, X is supposed to generate a set of sequences, and Y is simply some given order. So if you have a sequence already and you have another element of Y, then you can append that last element to your given list, and you get a list that's longer by one element. So yeah, this transformation here really encodes just the set of constructors for finite sequences. And similarly, this here corresponds to the set of constructors for finite trees. And in fact, you could say that the minimal fixed points that you get are precisely the recursive data types. So trees and sequences are clearly recursive data types. You can build them up by a recursive process. You can do induction over them. And this notion of minimal fixed point is something that you could precisely take as definition for the notion of recursive data type. Okay, now the big question, if we want to make this general, if we want to consider minimal fixed points of general transformations, then the big question is, what should these general transformations be? And the answer is, well, we already know which general transformations of ordinals we want to consider, namely the delators. So we simply transfer that definition to the context of partial orders, because now with sequences and trees, in the context of Kruskal's theorem, we are in the setting of partial orders again. And yeah, I don't want to spell this out, but it turns out that if you take the definition of delator and you adapt it in a suitable way, then you get something that we call WPO delators. So these are simply transformations of partial orders, more specifically well partial orders. And once again, they come with suitable support functions. So for example, in the case of a tree with leaf labels, the support of such a tree would simply be the collection of labels that are attached to its nodes. And now there's one new notion that I want to mention briefly is this notion of normality. So such a transformation of partial orders can be normal. And what that means is simply that if we have an inequality in a value of that transformation, so in an order W of X, if we have such an inequality, then it's required that any element in the support of this smaller element sigma is bounded by some element x prime in the support of this larger element tau. And this also has quite an intuitive meaning, actually. Namely, think of this here, this inequality here, as an embedding of a tree sigma with labels into another tree tau with labels. And for embeddings of labeled trees, it's usually required that if I send some node in this tree here to another node in this tree here, then the label at this node here must be bounded by the label of the image node. And that's precisely what this here says. It says that the labels in the smaller tree are bounded by the labels in the larger tree. Okay, but let's not worry about the details here. Rather, I now want to look at these fixed points of these transformations of partial orders. And as I said before, on an intuitive level, we can simply think of these fixed points as recursive data types. The general notion I want to call a Kruskal fixed point. And the Kruskal fixed point of such transformation W is once again a function kappa that goes from W of X to some X, where X is then this Kruskal fixed point, or this recursive data type. And you can see the requirement for such a Kruskal fixed point here. Let me just read it out, and then we'll look at an example that will hopefully make things more clear. So namely, I have an inequality between two values of this kappa. The element of the big argument smaller and it becomes if you look at this transformation orders into the 1 plus x times x. And can you still hear me? It says that my internet has some issues.
Yeah, now it's okay. Previously, there's a bit anyway. Maybe it's not very stable, but now it's okay.
Okay. This example, the transformation of 1 x and see that this transformation here is minus namely tree as and then we have a pair binary tree, a new binary tree by taking the two given elements of the pair as immediate subtrees of a new root node. And as that already suggests, a Kruskal fixed point of this transformation is precisely the set of binary trees. And this map kappa that we need from pairs of binary trees into binary trees is precisely what I just said. So you have a pair of binary trees and you can combine them into a new tree by adding a root node. And now let's maybe briefly reflect whether we can make sense of this equivalence here. So on the left side, you have a value of kappa, so something like this. And the question is whether this is bounded or, in other words, can be embedded into some other tree of this form here. And the right side should tell you when this is the case. And indeed, there are two possibilities. So in order to get an embedding of this tree into another tree of the same form, you can either embed the left subtree of the tree into the left subtree of the other tree and the right subtree of the given tree into the right subtree of the other tree and send the root to the root. And that's precisely what this inequality here tells you. And the second possibility is that you can embed this entire tree here into one of the immediate subtrees of the other tree. And that's precisely what this alternative tells you. Because the support of Tor, the support of the bigger subtree, of the bigger tree will precisely be the set of its two subtrees. And so this x here will be one of the immediate subtrees of the bigger tree. And if you can embed this tree kappa of sigma into one of the immediate subtrees of the other tree, then you can embed it into the full tree. So yeah, I mean, the general definitions are always a bit, take some time to parse, but really if you unravel them in concrete examples, then you will see that this is nothing else but the usual recursive definition of tree embeddings. And now I can finally formulate this main result that I was trying to get at, namely, well, similarly to what we had before, if you now have a normal transformation of well partial orders, then you always have an initial or smallest Kruskal fixed point, which I denote by T of W, and also this transformation of transformation W into fixed point T of W is computable. And now together with Michael Rathjen and Andreas Weiermann, we showed the following result. So two statements are equivalent, again, over this usual base theory RCA naught of reverse mathematics. But now it turns out that we need a little bit more. So we want to assume something that's called the chain anti-chain principle. But it's a relatively weak principle, at least compared to the other things that turn up. And one of these statements in this equivalence is once again pi11 comprehension. And the other part of the equivalence is something that we call a uniform Kruskal theorem. And this uniform Kruskal theorem says that if W is such a normal WPO delator, then its Kruskal fixed point T of W is a well partial order. So why do we call that a uniform Kruskal theorem? Well, that's because if you take, for example, the transformation of X into sequences from X, then you get T of W is the set of trees. And so in this instance of the uniform Kruskal theorem here, what you get back is precisely the usual Kruskal theorem. Also, maybe as a second example, if you take T of W, if you take W of X, as we had before, to be this expression 1 plus X times Y, then T of W is precisely the sequences in Y. And then as an instance of the uniform Kruskal theorem, you get what is known as Hickman's lemma. Hickman's lemma. So Hickman's lemma is precisely this statement about sequences that comes out of our uniform Kruskal theorem in this example here. And maybe it's also good to provide a somewhat more intuitive formulation of the uniform Kruskal theorem. So on an intuitive level, what the uniform Kruskal theorem says is precisely that Kruskal's theorem holds not only for trees, so the original theorem was for trees, but for all recursive data types. And if you formulate it that way, so Kruskal's theorem holds for all recursive data types, then it certainly sounds much more intuitive than if you well, need to have all that machinery of WPO delators and what exactly these fixed points are in mind. So this formulation, Kruskal's theorem holds for all recursive data types, also indicates that this might be interesting from the perspective of theoretical computer science. And it's indeed the case that the uniform Kruskal theorem, or at least a similar version, was first formulated by a computer scientist, namely by Hasegawa. So this has been considered before, but what is completely new is this reverse mathematics result, that this uniform Kruskal theorem is equivalent to pi1 comprehension. And another reason why I think that this is interesting is that Alberto Marcone has shown that statement 1, so pi1 comprehension, is equivalent to a result that's known as the minimal bad sequence lemma due to Nash-Williams. And this minimal bad sequence lemma, it provides, I would say, the most elegant proof of Kruskal's theorem. But if you just consider the usual Kruskal theorem, then it may be a very elegant proof, but it's not the most elementary proof. So the minimal bad sequence lemma by this result of Marcone is too strong, in a sense, for the usual Kruskal theorem. But our result shows that this too strong is only due to the lack of uniformity. So once you add uniformity, you formulate this uniform Kruskal theorem, then the uniform version of the theorem will actually be equivalent to the minimal bad sequence lemma. And I think that's very interesting because it shows that an interesting generalization of result from combinatorics really uses the full strength of this famous method that's being used in combinatorics. Okay, so now if I have maybe 3 or 4 more minutes, then I would very briefly explain the main idea of the proof and then give a conclusion. So once again, the crucial direction is from the uniform Kruskal theorem to pi-1 comprehension. And by the previous result, we know that we can obtain pi-1 comprehension if we can show that for an arbitrary delator d, this Bachmann Howard fixed point theta of d is well-founded. And the crucial step to prove this is to construct out of this given delator d, so d is a transformation of ordinals, a normal WPO delator w depending on d. So once again, d is a transformation of ordinals. So in particular, it only acts on linear orders. And now this w of d, it should act on partial orders. So we have to extend it in a sense from linear orders to partial orders. And that's not trivial because partial orders can be linearized, but they don't have canonical or unique linearizations. But it turns out that there is a construction which achieves this. So given d, we can construct such a WD and a natural family of order reflecting maps that send each of these orders d of x into the newly constructed orders WD of x. And once you have this family of order reflecting maps between d and w of d, you can out of these construct an order reflecting map of this Bachmann Howard fixed point theta of d into the Kruskal fixed point t of w. Now, there should also be a lower index d here, t of wd. I think this construction is interesting in its own right because it shows that the notion of Bachmann Howard ordinal from ordinal analysis and these orders that appear in Kruskal's theorem, and they are very intimately connected. That's something that was in principle known before, but it's another nice manifestation of this fact here. In any case, now that we have this order reflection here, we can apply the uniform Kruskal theorem. So the uniform Kruskal theorem tells us that this order, this Kruskal fixed point t of wd is a well partial order. And if you have an order reflecting map of a linear order into a well partial order, then you can conclude that your linear order is also well founded. So we can now conclude that the Bachmann Howard fixed point is well founded, and that will then give us pi-1 comprehension as we wanted to have it. Okay, so let me come to my last slide. So the main point, besides and above all the technical details that I wanted to make, is that it's very fruitful to consider transformations of orders rather than single orders. Namely, by considering these transformations, we can connect several areas of logic and mathematics. In this case here, proof theory, reverse mathematics, and combinatorics. And what's also very nice about this, I think, is that we can complement traditional ordinal analysis by more abstract and very elegant results. So here the point that I want to make is that ordinal analysis is concerned with very concrete structures that can be very complex on a combinatorial syntactical level. And that's one of the great strengths of ordinal analysis. I mean, if you can give a very detailed analysis of concrete combinatorial structures, that's wonderful. But I think it's worth to complement this by a more abstract view. And if you go into the more abstract, then you will certainly lose concrete combinatorial information, but you will also gain, I think, a certain maybe more general, more abstract, insightful results. And just to mention one specific example, so we have seen the definition of Bachmann Howard fixed point in this talk. And if you recall, then the definition had two crucial clauses. On the other hand, if you look at the traditional notation system for the Bachmann Howard system in ordinal analysis, then depending on the precise presentation, this definition will have about 10 recursive clauses. So it's 10 clauses against 2 clauses. And this tells you that, well, on the one hand, as I said, you lose concrete combinatorial information that's treasured in traditional ordinal analysis, but on the other hand, you also gain a certain simplicity and elegance that I find very nice. And finally, let me say that if you would like to see a bit more, then I would probably recommend to look at these two papers. They both have an introduction that's intended for a general logical audience. So yeah, if you're interested in this, then I think it's worth looking at these two papers, the first by myself and the second one together with Michael Rathjen and Andreas Weiermann. And then, yeah, it just remains to thank you very much for listening and for inviting me, and I'm looking forward to the discussion. Thank you.
Okay, thank you very much. Excellent talk. So any questions from the audience? May I ask a question? As you know, in reverse math, okay, so your talk connect the hardcore proof theory like ordinal analysis with reverse math, right? In reverse math, okay, in the past, people are interested in big five, but somehow we have now the picture is not so clear because there are lots of combinatorial principles which doesn't fit. So I was wondering, can you look at the big five from your fixed point or from proof theory point of view? Is there any support for the big five? Like we should have a linear measure of proof theoretic strengths of mathematical theorems, or it's just like a zoo, it's chaotic. I don't know. Let me repeat my question. So at least for me, I was debating the general picture of reverse math. So the big five offer a very clear, maybe oversimplified, but the zoo offer a chaotic one. So I was wondering, maybe from your point, your proof theoretic point of view, can you offer some clearer picture? Say, should it be like a ordinal is like a linearly ordered and well-ordered thing, or is just no particular pattern? I don't know whether my question was clear, but because ordinal analysis was so elegant that lots of theories you can correspond to an ordinal, and then everything become clear. So the big five is a bit artificial, but I was wondering whether maybe there is a way to look at the big five, and then you could give some support to the order of reverse math. Okay, sorry, but it's not very clear.
No, I don't really think that I can provide support for the big five. What is certainly right, as you said, is that the ordinals are linearly ordered. So yes, if you come from that direction, as I do in this case, then you probably tend to end up with statements that are linearly ordered, simply because you pull them out of these ordinals that are linearly ordered. I wouldn't say that this provides evidence for the big five. Let me maybe see two more things about this. So first of all, I have always been working on relatively strong statements. And I think many of these very interesting examples from the zoo, and not all of them, but many of them are between RCA and ACA. So in terms of logical strength, many of them are a bit weaker than what I have considered. So maybe that's also because I have, that's also a reason for which I have encountered fewer examples of that type. And then maybe one second thing is that if you only look at statements of very low logical complexity, so if you only look at pi01 statements, if you only look at consistency strength, then the picture is certainly much more linear than if you look at non-implications between pi1-2 statements, for example.
Mm-hmm.
Yeah, so many pi1-2 statements that are incomparable as such will have same or comparable, at least, consistency strength. But yeah, I don't want to go as far and say that this provides any justification for the big five. I don't know.
Okay, thank you.
Thank you.
So Chen, we should let the commentators to make statements, right? Or I don't know what is the plan. So Sam, maybe you should make some comments or.
Yeah,
okay.
Yeah, so you can see a little PDF in the chat normally.
Okay, should I maybe stop sharing my slides for the moment?
Oh yeah, that's fine. So my general beef with any of this is that it's hugely complicated and depends on coding. And as a sort of proof of concept, in the screenshot you see a fixed point formula, which is third order in the chat. It's very simple. It just says that, well, given any mapping from Cantor space to Cantor space, there's a kind of fixed point. So it's f of b is in B, and any element in B can be reached from below. That's the second clause.
Okay.
This is very simple, and this immediately, without much trouble, gives you ATR0, and actually full non-monotone inductive definitions in the sense of cleaning, if you do a little bit of work. So this is simplicity, this is naturalness, and yeah, this entire the higher order, third order is so complicated, and it's so this is more finitistic, more natural. That stuff just doesn't fly anymore. It is true that Kleene and the gang were not too good at getting down to the heart of the matter and making things simple. That is definitely true. But this kind of thing gives you ATR0 immediately and full non-monotone inductive definitions. It's essentially nothing. It's one sentence. There's one universal third order quantifier, and that's it. So I mean, it's all very nice that you can get pi1-1 comprehension this way, but this does not require complicated definitions of dilators or anything. It's just and yeah, full non-monotone inductive definition a la Kleene. There you have it. And yeah, I admit that again, Kleene and the gang, they weren't too good at making their stuff understandable. But generally, when Dach and I compute stuff, it's via Gödel's T. And when we show that something cannot be computed, then we go to the strongest notion of computability, namely that we can find, namely S1 to S9. So it's more of a negative kind of thing. If you can compute something natural in math, you can compute it in Gödel's T, which yeah, is pretty okay. And that's what I wanted to say.
Okay, yeah, thank you. So I can't comment on the screenshot, first of all, because I couldn't open it right now. But in any case, I'm not sure how much that really applies here, because, I mean, for example, this idea to construct arbitrary recursive data types out of continuous order transformations or transformations that preserve direct limits and pullbacks. Thank you. That's something that comes from computer science. And I mean, if you think from relatively concrete structures such as sequences or trees that are being studied in computer science, then that's already quite a big abstraction to consider these arbitrary transformations and their fixed points. So yeah, I mean, all that I want to say is that I think continuity, accountability arise very naturally in some of these applications that come in particular from computer science. And it's we do study statements here where we assume, for example, continuity, not because we want to somehow fit them into reverse mathematics, but because you simply can only construct these these fixed point, these recursive data types that appear in computer science if you have continuity. Sure, I mean, if you're looking at different examples, you will encounter different phenomena, but I would say it's still pretty natural here. And I would also say that, I mean, I mentioned before that sometimes when you have statements that are incomparable in terms of implication, they are very much comparable in terms of consistency strength. And I have the impression that this is still an interesting point. So sometimes when you get things that appear extremely strong in the sense that you cannot compute or you cannot prove them in a certain setting, then I would say sometimes this strength can be explained in a relatively simple way by saying, well, it's not due to logical strength. It's simply due to quantifier complexity. So it's simply because, okay, an object of a lower type cannot compute an object of this higher type, but once sort of the types match, part of this phenomenon may go away. And
well, not exactly, because you like this f is a third order object, right?
Hmm.
And even if you would say, well, this f is somehow computable in some comprehension functional, you couldn't compute this b in any sort of third order comprehension functional. You would need to go fourth order. That is, yeah.
Yeah, but whether that shows that the statement is super strong, or whether it just shows that somehow the setting is not the right one because it makes the statement super strong that shouldn't be, I think that's always up to debate.
Yeah, there I must agree. There you're right.
But
yeah, my point was more about simplicity. Look, this is about as simple as it gets, you know, qua fixed points, no dilators necessary, and yeah, it goes rather high up. Okay. And just because you allow, yeah, I mean, it's not even, you don't even have to say that third order things exist, you know, you just universally quantify over them.
All right.
And I do apologize for my predecessors that, yeah, they weren't very good at making things understandable. But now we do have it.
Okay, so we have another commentator, Juan. Please.
Yeah. So. Maybe I have some technical questions.
Please.
But I'm trying to determine whether I have something to say about the previous discussion.
I mean, maybe one thing that I do want to add is that I still think that sort of these more, let's call them concrete finitistic phenomena are still interesting. I mean, it's also interesting to study really what happens on the abstract, uncountable side of things. I really don't want to deny this. But for example, if you use, I don't know, abstract domain theory to prove something about the termination of concrete algorithms, then there is somehow a gap between these very abstract methods and the concrete results. And I simply find it very interesting to see how this gap is being bridged and what exactly it is that remains and that is being used from the strength of the abstract principles and this type of concrete applications.
So perhaps I would just say that the word complexity and the word simplicity could mean different things. And depending on what one wants to say, you should be careful on what one says about complexity or simplicity. Because I think that you had different goals in mind, and for different goals, different notions of complexity or simplicity are appropriate. For example, you could talk about how much time it takes to explain a concept to someone. And I don't know, dilators are a simple thing, I think. But then if one really wants to study them, it maybe takes a long time. And functionals seem more, maybe the same. I don't know. I think that dilators aren't very complicated, but that one should keep an open mind and not always look at theories and theorems the way that people have looked at them in the past. I don't know if I said anything. So maybe I can make some technical, ask some technical questions.
Please.
I imagine that the Bachmann Howard ordinal is a fixed point of some dilator.
Uh-huh. Yeah, that's probably gonna be true. So what I can say right now is that there has also been a result where the Bachmann Howard ordinal is relativized at a lower type level. So at one of these type 1 well-ordering principles. So you look at the notation system for the Bachmann Howard ordinal, and somehow you're allowed to throw in arbitrary constants, arbitrary epsilon numbers, but not, you don't relativize for transformation. And then what that gives you is omega models of bar induction. So that has been done by Rathjen and Valencia-Miscaino. But
so that's like something that you give it an ordinal and it gives you the next Bachmann Howard ordinal?
Something like that, yeah.
The same way that you can take an alpha and it gives you like the fixed point of the omega function starting at alpha plus 1?
I mean, it's not exactly the same, but yes. So more precisely what happens is you throw in an arbitrary given set of epsilon numbers, of uncountable epsilon numbers. And then you collapse these into the countable. And then what you get is the relativized Bachmann Howard ordinal. But what I prefer about this, about the higher type level that I showed, is that all of the specific syntactic details of the Bachmann Howard construction disappear. Just this general idea of having an almost order preserving collapse, that remains. But you don't have any epsilon numbers that you have to compare with sums of omega powers and so on. And that disappears on this level, but it doesn't yet disappear on the level below.
Uh-huh. So in general, if you have a dilator, and let's say it's alpha recursive, let's say it's an L alpha for some alpha. Yeah. Do you know how large the least fixed point for that dilator is?
So I think that if you are in alpha for admissible alpha, then alpha will be a Bachmann Howard fixed point. But there are also smaller ones. And I don't know how small the smallest is.
Right.
But the traditional picture is that when you construct the Bachmann Howard ordinal, just the usual Bachmann Howard ordinal, then usually as first approximation, you would show that the first uncountable ordinal gives you a fixed point. And then you will realize that actually I can do better, and actually already the Church-Fini ordinal gives a fixed point. But then you realize that there must also be recursive fixed points below it. And I would say that something very similar happens in the relativization.
Mm-hmm. Like maybe if you have an admissible alpha, and then there's a dilator around there, like a bit above alpha, then you get a fixed point before you get to the next admissible.
I think so.
It could still be that. So for example, you might ask, if you look at all the dilators in L alpha plus 1, whether the least fixed points for all those dilators have supremum the next admissible, or whether it's bounded.
Yeah. It's a good question. I don't know, but maybe one thing that I can say is that I think it's also very important to look at the contrapositives of the well-ordering principles, and they are sometimes more important than the actual statement. So maybe maybe to answer this, it's better to look not at the size of the Bachmann Howard fixed point, but maybe to consider examples where the Bachmann Howard fixed point is ill-founded, and then look at the first ordinal where you were given dilator fails to be a dilator. So the first ordinal where it doesn't preserve well-foundedness. Yeah, but I can't say anything more precise about that right now, I'm afraid.
So something I noticed about the proof is that it has a kind of a local flavor. So you go looking at the next admissible one by one. And this made me wonder, do you think that there's a similar principle for something like KPI?
I am pretty sure that there is, but it hasn't been worked out yet. So yeah, I think you can construct transitive models of any theory that you have an ordinal analysis for.
Yeah, it's nice.
Okay, any more comments or response?
Yeah, thanks for the very nice presentation. Yeah, I just have two questions. One is about the last theorem. The previous equivalence is work on the RCA0, and the last one is RCA0 plus the chain and anti-chain principle. So my concern is that, definitely this new principle is necessary. And what is the strength of this chain anti-chain principle? You showed the one direction of the proof to show that the uniform Kruskal theorem implies part one comprehension. Is that another direction use the chain and anti-chain principle? Right?
Yeah, so it's the direction from the uniform Kruskal theorem to pi 1 comprehension, where we use the chain anti-chain principle. And so the chain anti-chain principle is relatively weak. It follows from Ramsey's theorem for pairs. So it's way below arithmetical comprehension. So it's certainly weak enough to make the equivalence still interesting. And we need something that's actually a bit weaker than the chain anti-chain principle. Namely, what we need is that if you take the product of a well order and a well partial order, then the result will still be a well partial order. And it depends a bit on the definition of well partial order that you choose. So if you take the definition that I would say is most standard, then this cannot be proved in RCA not alone. But you can take other definitions. So for example, you can simply define a well partial order by saying that in an arbitrary sequence, you will have a increasing subsequence. And if you take that other definition, then RCA0 without the chain anti-chain principle will do. So it's simply that in the proof of this direction, we boot up in several steps. So the first step is we use this fact over. So in the talk, I said that Hickman's lemma is also an instance of our uniform Kruskal theorem. And Hickman's lemma is known to be equivalent to arithmetical comprehension, which is already stronger than the chain anti-chain principle. But in order to see that Hickman's lemma really is an instance of our uniform Kruskal theorem, we need to know this fact about products. And for this, we use the chain-anti-chain principle. And then once we have Hickman's lemma, we can move further up until we get a base theory that's strong enough for our purposes. So yeah, I don't know. I mean, I think it would be very surprising if the chain-anti-chain principle was really necessary there, simply because it's such a strong statement that we get, equivalent to pi1 comprehension. But we haven't been able to avoid it so far. And I've spoken to a few people, and yeah, it hasn't worked so far.
So do we know the strength of this chain-anti-chain principle in the big files is known?
It's rather weak.
It's
Actually,
to the side. It's one of the animal in the zoo. Below RT, as Anton said, below Ramsey theorem for pairs. Strictly below.
But in terms of provably total algorithms and consistency strength, it's not stronger than RCA0. So it's really quite weak compared to the other things that have appeared in the talk.
Okay. My last question is about the Gensen's prove that PA cannot prove epsilon 0 is well-founded. Does Gensen's proof use the Gödel's second incompleteness theorem, or he just a direct proof without the Gödel's second incompleteness?
Okay, that's a very good question now, and I'm a bit unsure because well, I don't know all of the historical details. What I can tell you is that there are at least two different proofs that come from Gensen's work. And one of them is a reduction to consistency. So this one does use Gödel's incompleteness theorem. But the other one, so I think I only know the modern formulation. If you admit a set variable as parameter, then you can really express well-foundedness, because then you can use this set variable to simulate universal quantification. And then you can show directly that if you have a primitive recursive relation that's well-founded as formulated using this set variable, then the order type of that primitive recursive relation, if it's provable to be well-founded in PA, then the order type must be smaller than epsilon 0. So this you can show directly by looking at the structure of proofs without using Gödel's second incompleteness theorem.
Yeah, my bigger concern is that for the skid or the proof in your slide, you say that the formulation of consistent PA is a bit different. For Gödel's second, he has to do arithmetization and then formalize the notion of probability just in PA, and he has the probability predicate, and then consistent PA just see that 0 not equal 0 is not provable. Where this probability predicate, but in your schedule of proof, your idea is that we label the different proof by ordinal, and if we have a proof of contradiction, and then we can have a label by a lower ordinal, and then we get a descending chain and the conclusion. It seems that yeah, my concern is that it seems that how to say. It's a different way to express the consistent PA. For Gödel, he how to say, he localized or formalized the notion of probability in PA, but it seems that your notion of proof is just is how to say, just a meta object just beside the PA. It seems for me it's different kind of notion of consistency. Yeah, this is my, yeah, when I say this case, this is my concern. Yeah, does anyone agree with this?
So I think what was kind of non-standard in the result that was more the definition of well-foundedness. So the definition of well-foundedness in that result, I said that I want to look at primitive recursive sequences only for reasons of formalization. And the definition of provability and consistency is standard in this result. So I don't think that there is a principal issue here. And what's certainly true is that if you want to work out all the technical details, then that can become a bit complicated, because then you have to translate back and forth between maybe sequent calculus formulations and Hilbert-style formulations. And if you sort of really want to convince yourself that all these things are equivalent provably in a weak Bayes theory, then that might be some work. But I don't think that there is a principal issue there. So I would say it's really the provability and consistency up to some technicalities that may be difficult, but no problems in principle.
Okay, I will look more at your slide. Maybe my misunderstanding anyway. Okay.
Thank you.
Okay.
So I have a comment about Gensen's proof, since you were asking.
Okay.
The way I understand, which I might be wrong about, is that Gensen never really talked about ordinals explicitly. That came afterwards from people reading his proof and understanding it and trying to generalize it. So he had two proofs of the consistency of PA, and both involved some cut elimination argument. And the second, one of the proofs, or both proofs, were by some kind of induction. And one of those was a bit more efficient in that if you look at the induction, you can abstract an ordering of length epsilon 0 from it. But I believe that this was realized afterwards by somebody else. And Gensen was just trying to get a proof of consistency, which of course it didn't appeal to, of course the proof cannot go through in PA. So he didn't explicitly prove that epsilon 0 was not provably well-founded in PA, but that was a consequence. And in the other one of his consistency proofs, it seems that the induction was actually longer than epsilon 0. So he actually proved consistency of PA using a longer Will ordering. And I'm not sure if it's known exactly how long it was.
Yeah, I don't know, because I haven't studied these historical papers in sufficient historical detail. But maybe just one thing to add. I mean, one of Gödel's papers is called Provability and the Unprovability of Cases of Transfinite Induction. So he was certainly aware that there is a connection with transfinite induction and somehow the ordinals. But how exactly he formulated his result, I don't actually know.
Okay, thank you.
So Juan, are there any references about this part of history, like Gensen's proof?
So at least one of the proofs is in Takeuchi's book.
Okay, proof theory, right? Okay.
I'm not sure if both are. At least one of them is. Putlak had a PhD student a few years ago who was studying one of the Gensen proofs and trying to determine what the length of the induction order was. And I'm not sure exactly what the results were. But I think she showed that it was longer than epsilon 0. But I don't really know exactly what the result is.
There's also a very interesting paper by Buchholz. I think it's called something like Explaining Gensen's Proof something, I'm not sure, where he shows how exactly to connect Gensen's original formulation with the more modern formulations, presentations of his ordinal analysis.